And welcome back to Anton Math. Now we're just going to do a couple more examples of this video of finding the powers of complex numbers and finding the nth roots of complex numbers, in both cases using that polar form and what we learned from DeMoivre's theorem. So first, let's take a look at finding the 10th power of the number root 3 minus I. So remember, the first thing we need to do is we need to turn this into a polar form. So if this is z to the 10, then first I need to find my r, which is my modulus of z. So that's going to be the square root of 3 squared plus -1 squared. Again, I know that I say this a lot, but it's a very common mistake. This is -1 because my b is the coefficient of I, and here I have a -1 I. Alright, make sure not to have any i's in here. So this is the square root of 3 plus 1, or the square root of 4, which is going to be 2. Now calculating out r to the n, which we're going to need to find this power, my r to the n here then is going to be 2 to the 10, and this is just what we had in the last example, isn't it? For all you computer science majors, this should be very familiar. This is 1024. Now the next thing I need to find to get this into polar form is I need to find my theta. So theta here, we don't know theta yet, but finding theta, we should say, we know that tangent of theta is equal to b over a, so that's -1 over the square root of 3, which we know is -√3 over 3. Now, I have that my a is positive and my b is negative. So I'm looking for a theta in quadrant 4. That's the only place I have positive a's and negative b's, where tangent is -√3 over 3. Now in quadrant 1, I have tangent of pi over 6 is √3 over 3, and the number in quadrant 4 with reference angle pi over 6 is theta equals 11 pi over 6. All right, now we're ready to go. Just a quick reminder, z to the 10 is going to be r to the 10 times cosine of n theta. I shouldn't say n, here my n is 10, so this is 10 theta plus I sine of n theta, in this case 10 theta. So plugging in my √3 minus I to the 10, we found our r to the 10 to be 1024, and I have cosine of 10 theta, so that's 10 times 11 pi over 6 plus I sine of 10 times 11 pi over 6. So we have 1024. This cosine of 10 times 11 pi over 6, that's cosine. I can simplify this a little bit, right? My 2 cancels, and this is 55 pi over 3 plus I sine of 55 pi over 3. So we have a little bit of work here to do. I need to figure out what cosine and sine are of 55 pi over 3. So let's try to find out what 55 pi over 3 is coterminal with that we're a little bit more familiar with. So I can break up 55 pi over 3 into increments of 2 pi. So let's take a look at that. Now, I'll draw a different color. 55 pi over 3. I'm going to write this as 54 pi over 3 plus pi over 3. Okay, let's see if this works out. Now I have something that's divisible by 3, so we're going to get some increments of pi here. And 54 divided by 3, or actually maybe I can do this a different way. I know that 54 is 6 times 9. So this is 9 times 6 pi over 3, isn't it? 9 times 6 gives me 54. So 9 times 6 pi over 3 is the same as 54 times pi over 3. So I have plus pi over 3. So this is the same as 9 times 2 pi plus pi over 3. Now any increment I add of 2 pi to an argument gives me the same cosine and sine values. So this, continuing with our problem, my root 3 minus I to the 10th, I have 1024. Cosine of 55 pi over 3 we found is the same as cosine of pi over 3. And I have plus I sine of 55 pi over 3 is again the same as sine of pi over 3. Okay, so this is our polar form answer where our angle is between 0 and 2 pi. So if that's what you're asked to find, this is it. But usually you'll be asked to find an a plus bi answer. So let's go ahead and take a look at that. That's 1024. And I want to solve now for cosine and sine. Now cosine of pi over 3 is 1/2 plus I, and sine of pi over 3 is root 3 over 2. And multiplying this through, half of 1024 is 512. So this becomes 512 plus 512 root 3 I. So here we have our a plus bi form of root 3 minus I to the 10. So a little bit more difficult of an example than our previous video, so this gives us some extra practice. Now let's take another look at an example of finding the nth roots of a complex number. Now we're going to take a look at what seems like a simple complex number, negative 27. Now I've written this problem a little bit differently. Instead of finding the third roots of negative 27, I've said let's solve z cubed equals negative 27. Now if this was an x, there's only one solution here, and it's negative 3. But because this is a z, we have complex solutions as well, so there's going to be exactly 3 solutions. And remember, the third roots of a number are the 3 numbers in which when you cube them, you get your original number. So we're really solving the problem, what are the cube roots of negative 27? So instead of using omegas here, I'm going to use z's, but first I need to find some things. I know that my r, this is equal to the modulus of my negative 27. This is the number we're finding the roots of. And when we're dealing with real numbers, modulus is just absolute value. This is 27, but to see why, I know this is the square root of negative 27 squared, isn't it? And negative 27 squared is some positive number, which has a positive square root of 27. So then my r to the 1 over n, in this case, is r to the 1/3. That's 27 to the 1/3. Now 27 is the same as 3 cubed. So I have 3 cubed to the 1/3, and that cubed and 1/3 powers cancel out, and my r to the 1 over n is just 3. All right, now we need to find theta. Remember, our next steps for finding the roots are to find theta over n, and find 2 pi over n. Okay, so my theta, this is one of those cases where I can't use tangent, right? If I use tangent here, I'm going to have, well actually I can use tangent. Let me take that back. Let's go ahead and use tangent. This is one of the cases we don't usually need to, but it's not a problem to go ahead and do it. So tangent of theta is 0 over negative 27. This is my b over a, so it's just 0. Now the reason we normally wouldn't use tangent here is because negative 27 doesn't actually fall in a quadrant, does it? This is just on the negative real axis. If we were back in polar coordinates that weren't complex, we'd say the negative x-axis. So we need to find where tangent is equal to 0, but my real value is negative. So my theta is not 0. My theta here is going to be pi. So we don't really have a problem using tangent. It's fine to do. I know tangent is 0 only at 0 and pi. And at 0 I should have some positive real value, so I must be at pi. But usually we can think this already. Whenever we have one of those values that are on the axes, we're very familiar with those thetas anyway. So now the next couple things we need to find theta over n. So theta over n here is, my theta is pi and my n is 3, so I have just pi over 3. And to find my following roots after my initial root, I need 2 pi over n. And 2 pi over n here is just 2 pi over 3. Okay, now we have all the information we need. Whenever you're doing a nth roots problem, this is what you want to do first. This gives you everything we need now to just write down the roots. Now my first root, and instead of using omega, I'm going to say z naught, because we're finding all the solutions for z in this equation, aren't we? So my first solution for z, this is r to the 1 over n, which is 3, times cosine of theta over n, which is pi over 3, plus I sine of theta over n, which again is pi over 3. Now to find subsequent roots, in our formula we're plugging in values for k, so this is when I plug in k equals 1, but remember if we go in order, all I need to do now is add 2 pi over n to the argument of the previous root we found. So this is going to be cosine of pi over 3 plus 2 pi over n, which is 2 pi over 3. And pi over 3 plus 2 pi over 3, well that's just pi, isn't it? So I have cosine pi plus I sine pi. And my final root, we should only have 3 of them. I still have a modulus of 3. And now I'm adding 2 pi over 3 to pi to get my new arguments. Now 2 pi over 3 plus pi is going to be 5 pi over 3. And then I have plus I sine of 5 pi over 3. Okay, we're done. These are all the values of z, which when we cube these values of z, we get negative 27. Now, you'll usually, in this case, be asked to write these roots in the form a plus bi. And the reason is because this problem is designed with nice angles that work out in a way that you can write them as a plus bi. So let's take a look. If we wanted to finish this out and write it as a plus bi, I have 3 as my modulus. And remember, all we need to do to go to a plus bi is plug in these values for these trig functions. Cosine of pi over 3 is 1/2, plus I sine of pi over 3 is root 3 over 2. And so distributing through, I'm going to get 3/2 plus root 3 over 2i. Now the second one is a little bit easier. Cosine of pi is negative 1. I have plus I sine of pi is 0. So my second root is negative 3. Now notice this is the real number root that we would have had if we were solving the equation x cubed equals negative 27. Any real roots that we have for a problem are also complex roots. Remember, real numbers are just going to be a special case of complex numbers where b equals 0. So if it's a root in the real numbers, it's still a root in the complex numbers, only now it's one of the many roots instead of being the only root. And doing this last one, writing this in a plus bi, cosine of 5 pi over 3 is a positive 1/2. And we have plus I. Now sine of 5 pi over 3, now we're looking at a negative square root of 3 over 2, aren't we? We're down in quadrant 4 now. So we have 3/2 minus root 3 over 2 I. Now these are my 3 solutions for z. So if we wanted to at the end, just to be clear, we could say z equals negative 3, 3/2, and I'm going to be a little fancier. I'm going to say 3/2 plus or minus root 3 over 2 I. I can use this plus or minus here because if it's plus, that's one solution. When it's minus, that's my other solution. All right, now that's it for complex numbers. In the next video, we're going to start our new section talking about plane curves and parametric equations. We'll see you there.